Okay, so this is ultimately review because it was in that play pause it video that was painful and difficult, okay, based off of your scores on it and based off of complaints I've gotten in past semesters. Okay? So don't stress about it. Okay? So before we start into it, equilibrium. What do you remember about equilibrium? What's that? Rates is a little bit dodgy to throw into equilibrium because rates are ultimately kinetics, and equilibrium and kinetics are looking at different things. Equilibrium is actually thermodynamics and kinetics. They're part of an energy diagram, but they're different parts of the piece. KAs. I heard stinks. Stable. Okay, so stability is a big thing with equilibrium. Okay. Most people think of equilibrium and think, oh crap, I don't want to have to deal with this. Okay. Unfortunately, we're now kind of to that point in the semester where you just kind of have to deal with it. Okay. I apologize, but that's the way it's going to work. Okay. Virtually every single one of the reactions we're looking at are equilibrium, which means they go forwards and backwards. Okay. Almost all of the reactions we've dealt with this semester were reversible. We just never really pushed that very much. This is the first chapter that it really shows up. Okay, so we're going to have to be kind of careful. So, when you go through and do these, what you should be trying is all of the pathways. Okay, and that can be a bit overwhelming because there's lots of different things that could possibly happen. So you should be trying paths to see where they dead end or where they go. Because maybe they go to a dead end. If you don't test the path now in your homework, guess when you test that dead end? During the test, and you've now wasted time. Okay? So I really want you to try to do all the wrong things with these reactions so that you can see where that takes you and you can recognize that that is not a valid path and you need to try something else. Okay? That said, there are some things that are so wrong you can't do. Okay? So don't break Lewis structures or curved arrow rules. Okay? So when we look at it, do not exceed octets. Do not lose octets, okay? Particularly on electronegative elements. Okay? Don't be setting up a system where an oxygen has 6 electrons around it. That's not going to happen. You screwed up. Okay? Move electrons from a source to a lac. Okay. Bonds to electronegative atoms, bonds to lacking atoms, atoms to bonds. One of the most common things that I will see within this chapter is people attempt to try and go through and draw out a mechanism because we're looking at carbonyls. Let's take a look at one. It is all too common to see this kind of an arrow. Okay. Because you're saying, oh, I'm going to making a carbon-carbon double bond with an oxygen, right? Fair game. I'm totally allowed to do that. No, no, no. No. Okay? You are not moving that pi bond in that fashion. Okay? What happens if you moved that pi bond in that fashion? What was the result?
Different compound?
The oxygen has 6 electrons around it. It's not formally negative. Okay? It becomes positive. Not only is it positive, it doesn't have an octet. That's bad. You can't do that. Okay? But that is probably the most common way to move from that carbonyl over to that structure. Because you know you want the enolate, so you just say, oh, I'm going to move the arrow, or move the pi bond. No. Where did the pi bond come from?
Electrons.
Which electrons?
The electrons shared between oxygen and carbon.
Oxygen and carbon is saying that that purple arrow is valid. It is invalid. That is entirely wrong. The electrons came from a hydrogen that was all too commonly implied. By moving the electrons in, what have we done to that carbon now? What's that? You've exceeded its octet. So now what has to happen? Those pi electrons move up to the oxygen. What's the result? We get a negative oxygen, and we have that pi bond now. Everybody see that? Okay. And you may think it's not that big of a deal. Well, when I provide the mechanism, it's a huge deal because your mechanism is wrong. Okay? It also becomes a huge deal if you have to propagate multiple steps thereafter, and you've now taken a shortcut that invalidated your chemistry. That invalidation of chemistry will come back and bite you because you won't be able to figure out how to move forward. Okay? And you'll start just adding and deleting atoms at will. Ultimately, a fancy way of saying guess. Okay? Even if it's 33%, 33% is not passing. Okay? We can even bump that up to a 50%. Okay? That's still not passing. Okay? So be very careful with your arrows. Move them appropriately. Okay? So, did you guys have any questions when you saw this slide in the video? Yeah, we had some questions. Okay, so our overall reaction, we start with an aldehyde. We have water. I want to end at that final structure. Okay, what should happen? Okay, we've got water as a nucleophile. Why'd you say water is a nucleophile? Okay, I just want to walk through that real quickly, and I'm sorry, I'm going to rip on you. Okay, told me water is a nucleophile, and I asked why is it a nucleophile, and you told me because something else is an electrophile. Did you address at all why water was a nucleophile? Oh, okay, cool. And I like that a lot better. And I understand where you're going with that, because that's good. You've acknowledged the carbonyl chemistry. We've talked about the reactivity of the carbonyl is that it is an electrophile. Once I have labeled that as an electrophile, now I'm okay with you saying water is a nucleophile. Did I spell that right? Close enough. Okay. Why would it act as a nucleophile? It has lone pair electrons, so it can act as a nucleophile. Okay. So if it acts as a nucleophile, what does it do? Donates electrons. What's it going to donate electrons to? The electropositive site. Good thing we identified it. We would exceed the octet on the carbon, so now what happens?
The pi bond breaks.
We break the pi bond. Okay. What is the result of that? There's our new bond. And if we account for all of our charges, that's what we end up with, right? Is that a yes?
Yes.
Okay. Is that a likely thing to happen?
No.
Why not?
You have a positively charged oxygen.
I have a positively charged oxygen. I can't have positively charged oxygens. H3O plus doesn't exist.
Well, that positively charged oxygen is going to want to leave.
Okay? So the suggestion is that positively charged oxygen will want to leave. It'll want to take those electrons. So what you're suggesting is it will leave, generating equilibrium. Yes, that is perfectly valid. Okay? So you're saying it's unstable, I want to fix it. Does that structure, should it exist? Okay, H3O plus, right? H3O plus is what? I heard that. An acid. Okay. While it may not be one of our memorized strong acids, its pKa is negative 1.7. So it's a strong acid. Okay, we may not have memorized it. That's a strong acid. Okay? Why might that be a problem?
Because that means that that's a strong acid. Probably.
That the structure up there is probably a strong acid. Why is that a problem? Depends on the conditions, which at this point we didn't specify.
H3O+ is a strong acid. Water is a weak nucleophile.
True, not ultimately that big of a deal. We still look at that structure we drew. We're saying that part of that structure is a strong acid. Part of that structure.
So it's going to give up the hydrogen?
It would give up a hydrogen if there was something remotely basic around.
Negatively charged.
There's a negatively charged oxygen. What is a negatively charged oxygen? We've seen that in the same form of something like hydroxide. It's what?
It's a strong base.
It is a strong base. So in the course of this reaction, I made a strong base and a strong acid at the same time. Is that a good thing? No. That structure is insanely unstable. Okay? So much so that that strong base is going to neutralize as quickly as possible because I don't want to have the strong base in the presence of the acid. That acid is so acidic that it's going to neutralize as quickly as possible because I don't want it to be near a base. So what ends up happening? The reaction goes backwards. Is this reaction likely to happen? No. If I still want that final structure, I need to change this reaction somehow to get to that final structure. Okay? And we've kind of addressed it. We said something about conditions. Yeah. What were the conditions at this point?
Neutral.
It's neutral. And under those neutral conditions, that first step says no. Which means we don't make the product. So I could change the mechanism. Okay? To change the mechanism, I have to change the reagent conditions. Okay? I still have a nucleophile and an electrophile. In the change of the mechanism, what I want to do is to make one of those more reactive. That makes it go faster. Well, which one do you think I want to ask about? Okay, the aldehyde, which was what? The electrophile. Or water, which was the nucleophile. Which one do you think I want to talk about? Why do I want to do the nucleophile? Because it says it on the top of the slide. Yes, that's where my focus is right now. Could I also change the electrophile? Yes. Okay. Use all of the cool tools at your hand. The tools here say we want to speed this up by making the nucleophile stronger. To make a nucleophile stronger, what needs to happen? It needs to become negative. How do I make water negative? I need to take away one of those hydrogens, which means water is acting as? It would be acting as an acid, which means what do I need to react that water with? A base. I add the base, that removes the hydrogen. My very first step is the formation of hydroxide, which is now a strong nucleophile. As a strong nucleophile, what is it going to do? Now it can attack the electrophile. We can break the pi bond. Agreed? We ran this under what kind of conditions, acidic or basic? Basic. What charge was a base?
Negative.
Negative. What charge is a nucleophile? Negative. If I want to make the nucleophile more nucleophilic, what conditions should I pick? Basic situation. The ending green structure now, is that better than what we had before?
Yes.
Because?
There's a more stable charge on it.
That negative charge is more stable
Than a negative and a positive.
than a negative and a positive. So is the negative more stable? No. What's the more stable part of this structure?
The alcohol.
I don't have a positive charge. That's what makes it more stable. Okay? Now what could happen? David.
You could add an acid and protein.
Okay? I could potentially add some source of hydrogen, protonate, and I would get that final answer. Okay? It could be in the form of actually adding an acid in a workup. It could also say that we're saying H from the solvent. What solvent? Well, if I had hydroxide, what do you think the solvent was? H2O. Okay.
So hydroxide is strictly act as a nucleophile, it wouldn't try to act and pull off an H.
Okay. So there's an interesting question, depending on how far you've read into the textbook. Okay, you might encounter, couldn't the hydroxide also act as a base and remove a hydrogen? Okay. So let's chase that tree a little bit. We want to get rid of that. We've just got the hydroxide. So there's all of our structures. Where would the hydroxide react as a base? What hydrogen could it remove? And if it helps, I can throw in some colors. We've got a purple H. We can call it a red H from our water. Call it a blue H down here. All right, we could even go, hey, there's a purple. No, I can't use purple. Let's make it orange. Which of those hydrogens would be likely to be removed, or least likely to be removed?
The blue one.
The least likely one to remove would be the orange one, because
It's already hydrogen deficient.
I don't quite accept hydrogen deficient.
You would make O2 minus, which is
If you remove H plus, you would have O minus 2. O minus 2 is even more reactive than O minus. Okay? Remember, our reactions should drive to more stable, not less stable. Okay? What other hydrogens could we try and remove? So we said not that one. So we got blue, red, and purple.
red doesn't work
Why not?
because if you do that reaction out, you get H and OH. So you essentially run really, really fast to get absolutely nowhere.
If the OH acts with the red hydrogen up here, what do we get? We get H2O and
OH minus.
OH minus. Does that not happen?
Yeah, it happens.
It absolutely happens. It's a perfectly valid thing to do. Does it go anywhere? No. Okay. Which means, let's not look at that one.
The purple
Okay. So we got two choices, purple and blue. Why'd you avoid blue?
because you would have two negatively charged oxygens.
Blue doesn't make a lot of sense to remove because if I remove the blue one, what would happen? That oxygen becomes negatively charged. And I'd now end with a structure that has two negative charges. Is that more or less stable than where I started? That's less stable. That doesn't make sense. Okay? So then that means it must be the purple one. Okay? Which when you ask the question, Christian, I'm going to bet that's what you were talking about. Right? And then I opened it up and just said, go to hell, answer all my hydrogens. Okay? So let's remove the purple hydrogen. Okay? So let's draw the result if we removed the purple hydrogen. Okay, so let's erase some arrows in here. Those electrons then go to the carbon, right? Everybody agree?
Yep. And then the double bond breaks.
Okay. I don't want to move the double bond yet. Okay. All I'm doing is removing a hydrogen. Removal of a hydrogen does not mean any bonds have to move except the bond to the hydrogen. So I'm now putting a negative charge onto that carbon. Can carbon stabilize a negative charge? No. Okay, so right off the bat, we should be like, Christian, you're wrong. But why were you maybe thinking like it's okay? Okay. A bunch of other people shouted out, ooh, resonance. What resonance?
Just put a double bond on hydrogen, just call it a day.
Unfortunately, yeah, putting a double bond to the hydrogen would call it a day. That would effectively mean that you're just done with OChem. Hydrogen can only have 2 electrons around it. We can't put a pi bond there. So the electrons can't go there. We could try and put it up here. Okay? What would happen then? 1, 2, 3 bonds. You'd be like, dude, totally did not exceed the octet, Mike. What's your problem? There's another atom. That oxygen has 10 electrons around it. Yeah, you can't do that. Okay? You've exceeded the octet by doing so. Well, then you can be like, well, you just didn't do resonance right, because once you move those electrons there to make that bond, you have to move those. The only reason you move a pi bond is because other electrons came and pushed it out. Those electrons, that negative charge, and the blue pi bond or the blue arrow pi bond are, guess what? Everybody loves this explanation. They are in perpendicular orbitals, which is a really fancy way of saying they don't resonate. Okay? To do resonance, seriously? Fine. Just to do resonance, I have to have p orbitals that are all in alignment. So there, the green can resonate with the red. What happens if I turn the middle one? Can I do resonance anymore? No. There's no orbital overlap, which means no resonance. Okay? When we look at that negatively charged structure, our electrons are in an sp2 hybrid orbital. The pi bond is in a p1. The sp2 and p, perpendicular orbitals. They don't resonate. It doesn't work. Okay? You don't like that answer. That's perfectly fair. I understand that because that gets into the hybridization part, and that stuff can just be crazy difficult to manipulate. Okay? So let's push it a step further. Okay? Let's just say, you know what, Mike, your hybridization sucks. I don't care, because if I go through and do that, I fix the problem. I remember where we started. What did we say we did? We did this, and then we did this. What would that end with? That's the structure. And you'd be like, see, the carbon has not exceeded the octet. Dude, there's another freaking atom. Okay? This comes from being like, oh, I'm just going to delete that because it's bad. It's bad, so you shouldn't have formed it. You don't just start deleting stuff from your structure. That means your mechanism to get you to that structure was false. You have to reset. Okay? And that is challenging to deal with. Okay? One of the biggest reasons why you're removing a hydrogen, which is very often implied, so not there. You're moving electrons. You're moving electrons, okay, which are also very often implied. Okay? So you're going to lose track of all of those things, and unless you're very careful with your counting in each of those cases, you're going to start to make mistakes and start to do things like that. Okay? Does the ACS think you're going to make those mistakes? Hell yeah. One of their answers is going to be that negative carbon that doesn't exist acting as a nucleophile. And then you will box in that answer incorrectly. Okay? Does that make sense? So you have to understand what hydrogens are allowed to be removed and when. Yes?
You still have to fix octal and carbon now, because like you've done double that.
I didn't even address the carbon in that statement, which is what David's trying to address here. How many electrons are around that carbon now?
6.
6. I'm missing an octet. So not only have I exceeded the octet on the oxygen with my drawing, I'm also missing the octet on the carbon. Everything about that structure is awful. Okay? When should you have discovered that the aldehyde hydrogen is not acidic?
Yesterday.
Last semester. Okay? And I'm not trying to pick on you, but that's when it was addressed. And that you should have drawn these structures to very quickly realize that it didn't work. But that involves hybridization. That involves resonance, both of which are concepts that students struggle with in first semester. Here's where it comes back and bites you. Okay? So, Christian, I want to say sorry, number one, because I just ripped on you for like 10 minutes. And then number two, thank you, because we needed to address that. Okay? And the only time I address that is when someone actually asks. Okay? Does that make sense? So when you go through and run these reactions, you will have a species that can act as a nucleophile or a base. You have to play around with it to decide what goes on. Okay? With this question, we could still have our base, our hydroxide, act as a base with other structures. And we'll see that at the tail end of chapter 18, which might be your other reference of where you were potentially going with that, is that you've read far enough into chapter 18. This starting material makes that unnecessary to evaluate. We will evaluate that later. Okay? Did I have to make the nucleophile stronger?
Yes. No. Well, water is not a strong nucleophile.
Okay? So we could have made water a stronger nucleophile by adding a base to make it a stronger nucleophile. Did I have to make the nucleophile stronger to make that final product?
Yes.
Why no?
When we had the unstable one that had the positive and negative formal charge, it could react with another of the same species.
The one that had the positive and negative formal charges in it, what you're now addressing is it could continue to react. But if that structure isn't stable, it never forms. I don't care what it does after the fact. It doesn't exist. To run a reaction, how many pieces do you need? Particularly this reaction. Rhymes with?
2.
There are 2 pieces in this reaction. You just tweaked the nucleophile. Did we have to tweak the nucleophile?
No.
What could we have tweaked?
The electrophile.
Okay? I want that carbon to become more positive. How can I make sure that that carbon has less electrons around it? I would want that oxygen to suck the electrons away from it. I want this to happen first. But then we'd have oxygen as a negative charge. That's not good. So how could we convince the oxygen to suck electrons away without becoming charged?
Acids.
Let's add an acid. What happens if we add H+? What's going to react with that H+?
Your electrons on your oxygen.
The electrons on the oxygen. The result, I get a positive oxygen. Does oxygen want to be positive? So what does it do?
Picks up the nearest electrons.
Where are the nearest electrons?
Pi bond.
In the pi bond. And
Your carbon is more positive.
now your carbon's a more positive atom. So adding an acid can now make the electrophile more electrophilic. Okay? How easy is it to reverse an acid reaction?
Really?
How easy is it to reverse a base reaction? The same, because when we talk about them, it's not acid reactions and base reactions, it's
Acid-base.
acid-base reactions for a reason. They are very easily to reverse, or very easily reversed, which means the mechanism or our reaction arrows for all of these are
Reversible.
reversible. So we would have to take into consideration that reversibility through the entire mechanism and decide, is that enough to shift to form products or not? Okay? That's where this chapter becomes challenging. Okay? So there's our nucleophile. We can make the electrophile by adding an acid. Okay? Note here they don't show the resonance. Why not? Personally, I think they're being dipsticks. They should be showing the resonance. Okay? They should show that that carbon is now more electrophilic than where it started. Okay? If we look at it as an energy diagram, the very first one we drew out, we formed that structure that was doubly charged. That doubly charged structure is insanely high in energy, which means the activation barrier for that first step is insanely high. So to Rob's point, once I make that, I can do all sorts of cool stuff, but I can't make it because the activation barrier is too high to get there. Okay? What happens if I shift to, what did we do first? Basic conditions. I'm no longer doubly charged. And in fact, if I compare, I form a negative oxygen. What did I start with? A negative oxygen. That reaction is effectively same energies. There's a name for that. What is that? I don't remember what it is. 152 stuff, right? A K of 1. That's all I got.
First order.
No, wrong expression. Okay? If we go into acidic conditions, we get the same system. Okay? Protonated versus protonated, positive versus positive. Different structures, same energy balance. Okay?
Did you look at the PKAs to determine the
You can evaluate pKa's for which of these three?
The acid.
You could look at the pKa for the acid one. Okay? The pKa for that structure, I don't know offhand, but I think it's about negative 1.5. And the pKa for that one is
16.
negative 1.5. Okay. Admittedly, I did just make up one of those, if not both of those. Okay. The pKa's are going to be roughly the same. Okay. We can't use pKa's for the middle one because those are basic conditions. We could look up pKb's. How many of you have memorized pKa's? Okay, if you haven't memorized the pKa, I'm really going to doubt you memorized the pKb. Okay? On top of which, is it necessary? Okay. If we go through and look at this, we've got a positive oxygen versus positive oxygen. Charges are the same. Size is the same. Electronegativity is the same. There's a little bit of resonance difference with this first one, which might make it a little bit more stable. If we really refine this, I think Carty took that into consideration. It is ever so slightly staggered. Okay? So could we use the rules that we've been using of charge, size, electronegativity, resonance, induction? Yeah. Those would still apply. We don't need to look up pKa's. pKa's would be more correct, but also more time. Okay? What we went through and formed, sorry, as I backtrack, at the end of both of those reactions was this final structure over here. It's known as a hydrate. Why is it a hydrate?
It's got water in it.
We added water to the structure. That was it. Okay? So if we run the reaction with water, we end with a hydrate. Okay? Are there other reagents that supply that same basic piece, that H and that OH?
Yeah.
Yeah. What other reagents?
Mg.
No.
And then H3O plus.
No. That didn't have the oxygen at all in that statement. So Mg,
Well, you used both of them.
technically you did. You said H3O plus, which was this reagent. And the MgBr was an entirely separate molecule, which had nothing to do with it. So what other reagent gives you an OH? And maybe I understand where you're going.
HGOAC.
How about just an R group there? Where R is any carbon group. CH3. What structure am I talking about? An alcohol. Okay? Where you were going with the Grignard maybe is you were saying, where could I make that? That's not what I was asking. It is kind of what I said, but that's not what I was asking. What I was asking is what functional group would give us those pieces. So instead of adding water, we could have added any alcohol. Any alcohol would have run a very similar reaction, except at the end of it, would I have hydrogens on my OHs? No, what would I have? I would have that R group. It's no longer a hydrate because I didn't add water. So we have to call it something else. We could call it an alcoholate, which sounds stupid, so we didn't call it that. We call it an acetal. Why? Because alcoholate was worse. Okay? So we can take our carbonyl, and instead of starting with water, I can start with an alcohol. The alcohol will then have to react twice to form the acetal. At the same time, it's going to kick out water. Where did the oxygen come from to make the water?
The base.
No. From the what? I kind of accept aldehyde because we looked at aldehydes initially. We don't accept aldehyde here because this is a ketone. Where did the oxygen come from? It came from the carbonyl. That oxygen for our water came from the ketone. Where did the hydrogens come from to make the water? Those came from the alcohols. Nothing happened to the alpha carbons. It came from the alcohol. So what we're doing is removing 2 hydrogens from our alcohols, and we're combining them with 1 oxygen from our carbonyl. If I remove those hydrogens, what charge would the oxygens become? Negative. So I would have RO minus, RO minus, right? If I remove the oxygen from the ketone, what charge would my carbon become? Why positive 2? I removed that oxygen entirely. Where are the electrons in the bond of that carbonyl going to go? They're going to go to the electronegative element, being oxygen, which would mean the carbon would become positive 2. Is a positive 2 stable? No. What would it need to hook up with? some negatives that I just generated from the alcohols. Okay? That's the basic pieces behind this. All of that comes from just looking at differences in electronegativity and just really applying the basics of the reactions. Okay? Are we ever going to form that +2? No. What we're trying to evaluate is where are the pieces so that we can see how this thing can work. Okay? What ends up being our nucleophile in this equation? Define nucleophile.
Electron rich.
I'll accept that. Electron rich. Okay, but we could have an electron rich species that doesn't act as a nucleophile. To act as a nucleophile, what must it do with that electron richness? It must donate. So it's an electron donor. Which species is my electron donor? The oxygens. Okay, which species is the electrophile? Our carbonyl carbons. Okay. Equilibrium. What do you think? The equilibrium question becomes a really challenging one to deal with.
Favors the products.
Okay? It is ultimately going to favor the original products. Original starting materials, our original reactants. Okay? The explanation behind that we'll have to dig into a little bit later. Okay? But first, we want to address those pieces. We've got this new functional group that we'll call an acetal. Okay? That is ultimately not stable and reverts back to that carbonyl state. Okay? In the process of the reaction happening, the first thing that happens is our oxygen can come through and attack. Okay? That causes the bond to break open. That would generate our di-charged species, right? We'd have a positive oxygen and a negative oxygen in the same structure. So we would be very careful to make sure that we either acid or base catalyzed this to make sure that we didn't form that and ensure that the hydrogens were placed accordingly. Once we've formed that, we don't have the full acetal because I need the other oxygen to attack. I'm roughly halfway to becoming an acetal. What is half of a circle? A hemicircle? A hemiacetal is halfway to becoming an acetal. It's an intermediate stage. What has to happen in that last step? A sequence of a couple complicated things, but number one, the oxygen for sure has to connect to the carbon, and I for sure have to eject that OH.
You said this isn't favored.
Okay? This is not a favored equilibrium. True.
All the electrons.
It's not all the electrons. It's a fairly complicated aspect that we'll look at. Okay? So, if we tweak the nucleophile, we make it basic conditions. Note, what did I do to change to make this basic conditions?
Remove the hydrogen.
Okay? On the alcohol starting material, I made sure to remove the hydrogen. It's now a nucleophile. And in particular, what kind of nucleophile? A strong nucleophile. Is it stupidly strong?
No.
How do you know?
It's charged oxygens.
It's oxygen, and our stupid strong are
Carbon and hydrogen.
carbon and hydrogen. Okay? So it's just a strong nucleophile. It's going to attack our carbonyl. We break the pi bond. Okay? We'd form our charge structure. Okay? I need to protonate that oxygen. Okay? Notice, what am I protonating it with?
The alcohol.
Alcohol. I'm not protonating it with an acid. Why not?
Because you neutralize it.
I was under basic conditions. I can't protonate it with a strong acid. I have to protonate it with a weak acid that's floating around in solution. That's going to be my starting alcohol. Okay? The result of that is what? What did I make? I've made my hemiacetal. Yeah, I realize I just butchered that spelling pretty horribly. And I reformed a nucleophile to go through and now attack. Okay? So let's take a look at that next step. Okay? What would need to happen? Well, a strong nucleophile would need to form a bond with the carbon. And at the same time, it has to kick out a leaving group. The leaving group that it has to kick out needs to be the OH. Could it have been the OR?
Yes.
Yes. What would it have done if it kicked out the OR?
Reformed essentially the exact same.
Reformed the same compound. We don't see anything useful. Is that still possible? Absolutely. Okay? But it doesn't change our structure, so we don't focus on it. So the OR attacks, kicks out the OH minus. Is OH minus a good leaving group? Okay? So I heard a no, and I heard a for those conditions.
Oh, yeah.
What are those conditions?
Basic.
Its basic environment is OH minus okay in a basic environment. Yes, that does not make it good. For the reaction to run, the product must be inherently stable. Okay? Is that structure inherently more stable than where we started? Not really. So that should raise an issue about that last step not being very likely. Okay? And if we go through and take a look at it, we kind of see that with the arrow. Because I'm hinting that it isn't a strict equilibrium, that this is actually going to revert backwards, and we end up not forming the acetal. Okay, which is true. We don't get a large concentration of the acetal. Okay? I gave you one answer. You should be able to give me another.
You haven't, when you do that reaction, you get, if you look at the energy on both sides of it, it's an O minus on both sides.
Which we just kind of evaluated. The balance of your energetics is not particularly favorable. Okay? It's also not disfavorable.
You've got two electronegative elements.
Pause.
attached.
Okay? What kind of reaction happened in that last step?
Nucleophilic attack.
And SN2 reaction.
Substitution.
Okay? It's a substitution. We've got a nucleophile. We have a leaving group. And we have a substrate, right? So this is just strictly a substitution reaction. Okay? When we run substitution reactions, do they all follow the same type of mechanism? No. And in fact, how many mechanisms are you guys aware of? Two. Conveniently called SN1 and SN2. So looking at those materials, which mechanism do you think it should do? Why SN2? That strong nucleophile is really telling you that you're running an SN2 reaction. And that is a phenomenal observation. That is exactly where you should start that. What substrate do you want for an SN2 reaction? Primary. What substrate do we have? Okay. And I'll admit, this one gets a bit tricky depending on how you define primary, secondary, tertiary. If we follow the strict definition of primary, secondary, tertiary, this substrate is officially secondary because it is connected to two carbons. Okay? If you go all the way back through my first semester lectures when we talk about primary, secondary, tertiary, and even through some of this semester's lectures, you'll notice that I kind of waver on those labels of primary, secondary, tertiary. And I tend to not label them based off of the strict definition, the number of carbons. I label them instead based off of the intent. The intent of primary, secondary, tertiary is to reference the stability of whatever that center atom is. Okay? And in particular, how that stability is different than if they were all hydrogens. When you first encounter primary, secondary, tertiary, it's when you're talking about alkyl halides, which means what are the atoms around your substrate atom? Carbon or hydrogen. So when you're told primary, secondary, tertiary, we tell you, oh, it's the number of carbons. A better definition is the number of not hydrogens. For those of you that just went glassy real quickly there, okay, that's why we don't use that definition. That definition is better suited here. Not hydrogens. How many not hydrogens are around that substrate? We could make the argument it's 4, and as was pointed out to me, it's never going to be 4 because one of them is the leaving group. So it's not 4. How many are there? 3. So we have what is effectively a tertiary substrate. Should the tertiary substrate react under SN2 conditions? No. That step does not happen under basic conditions, which means if you see a carbonyl under basic conditions, do you make an acetal? No. Okay? Which is a very common question. Here's a carbonyl, here's base conditions, and one of your answer choices is an acetal. You do not form it. Okay? That reaction is energetically flat. Okay? And then as far as the actual mechanism of how it happens, it's so sterically hindered that it prevents that reaction from happening. Okay? We do not form the acetal under basic conditions. So if you were given those conditions, what should you say is your answer?
The semi-acetal?
You just keep wanting to make it semi, don't you? Our hemiacetal. Okay? Our hemiacetal ends up being the answer. Okay? Well, if acetals are such a big deal, and I can't make it under basic conditions, why the hell did we talk about acetals? Because what happens if I switch it to acidic conditions? Okay. Under acidic conditions, the mechanism changes. Notice this mechanism was really 1, 2, 3 steps. That was it. That could theoretically get us all the way to the acetal. The third step never happening. Okay. If we switch to acidic conditions, we get a few more steps. Okay? And we jump up to 1, 2, 3, 4, 5, 6, 7 steps. Okay? At its core, we're doing the exact same thing that the base conditions did, but we also now have to do some extra acidification steps. Since we're running under acidic conditions, the acid is going to affect the electrophile. So the very first step is an acid-base reaction that does what? Activates our electrophile. Activates electrophile. What can then happen?
Your nucleophile can attack.
Now we get the nucleophilic addition. Okay? Now that I have a really good electrophile, my weak nucleophile can attack. Once the weak nucleophile attacks, I then form this structure, that piece right there, which is now a phenomenal leaving group. Because it is such a good leaving group, what could happen? That oxygen could bring its electrons down and it kicks out the leaving group, thereby doing what?
Nothing.
The reverse of what we just did. That sucks. That's why we show an equilibrium arrow. Okay? So I want to nullify that leaving group's ability. I need to make it less of a good leaving group. I can do that by pulling off a hydrogen. So doing an acid-base step. Okay? So we call this negate leaving group. We would now have the hemiacetal. Since we're still under acidic conditions, what happens? we can protonate one of those oxygens. Well, which oxygen? If we protonate the alcohol one, what did we do? We made it a good leaving group. You mean we went backwards? Yep. So that's not very useful. Let's protonate the alcohol. If we protonate the alcohol, now we have a good leaving group as far as water goes. So we've now activated a leaving group. Because I don't have a strong nucleophile, there's nothing to force the leaving group off. But it's a good leaving group. So what could the leaving group do? It could leave. Mechanistically, that's known as a heterolysis. Okay? Or leaving group leaves. For the record, leaves begins with L. We would form a carbocation. Are carbocations stable? No. Well, if the carbocation's not stable, then that step can't happen. Is this carbocation stable? Yes. Why? Resonance from that oxygen. We're effectively a tertiary carbocation. The tertiary carbocation with resonance stabilizes that long enough that now the weak nucleophile can do its attack. That nucleophilic addition, which is a little bit weird because it's actually shown here as a coordination, or nucleophilic addition, depending on how you've drawn out your reaction, is then followed by another acid-base step to remove that last hydrogen so that we no longer have a good leaving group. Okay, so this negates our leaving group through an acid-base. And what do we end with? The acetal. Okay. I think only one person that I've talked to said they were interested in potentially synthesis. Okay? That one person can probably ignore most of this because you probably won't see it again. The rest of you are probably aiming for pharmacy, PA, or med school. Okay? Under those three conditions, you're looking at carbohydrate chemistry. Guess where acetals are? Every single carbohydrate is an acetal, okay, or a hemiacetal. So you would need to know how to interchange between your acetals and hemiacetals so that you know the differing states for all of your carbohydrates. Okay? Starts with a carbonyl. If I add one equivalent of alcohol, I go to the hemiacetal. I add a second equivalent of alcohol, I go to the acetal and water. To reverse the process, what do I need to do to add to the acetal? I add water, that's it, and it reverses the process. Okay? This is such a heavy equilibrium, okay, or such a balanced equilibrium, if we want to think of it better that way, that it doesn't form acetals at very high yields. So how could I ensure that I get as much acetal as possible?
Take out the water.
I could remove water through the course of the reaction. Okay? If I remove products, the equilibrium shifts to make more products. What else could I do?
Add more.
Yes, what we're talking about is the application of Le Chatelier's principle. I could add more.
Of the reagents.
We have to be a little bit careful with that. It's not add more of the reagents. It's add more of one of the reagents. We typically add more of the alcohol, not more of the carbonyl. Why?
Because the alcohol is limiting.
No.
The alcohol is what?
The alcohol is cheaper.
Did I say that?
Okay? Cheaper, and it's easier to pull the alcohol out than it is the ketone or the aldehyde. Okay, so we almost always add an excess of the alcohol, and we also almost always try and limit the presence of water, if not remove it, to try and force that reaction along. Right? Say that again? We can play around with the heat, but remember, this is such an even equilibrium that it's not exo or endothermic, which means changing the heat doesn't really do much except increase the speed at which I achieve equilibrium. pressure and volume is an interesting question. What you're talking about changing with pressure and volume is which factor, though? Think back to thermodynamics. When we change pressure and volume, what do those change in thermo? You're like, what the hell? Don't worry. I didn't expect anybody to know the answer. 152. Entropy. So if you change your pressure or volume, you're really playing with entropy. Right? How much of an effect does that have? Well, if we try and look at this to go strictly from the carbonyl to the acetal, the carbonyl and 2 alcohol molecules to the acetal and water, we're going from 3 particles to 2. If I increase the pressure, which way is the equilibrium going to favor?
Reactants.
If we increase the pressure, do I want more particles present or less? I want less. So increasing the pressure is going to push more towards the acetals. Okay? So we could play with those. How big is entropy? It's very, very tiny. If you look up your tables of enthalpy values, they're usually kilojoules. Entropies are joules. So it's a factor of 1,000 difference. So yes, you can play with pressures. It usually isn't a big enough difference to make anything useful. Okay? So, which side is favored? Okay, this is ultimately a review slide. If we take a look at this top one, energetically the acetals are favored. Why? The aldehyde is that reactive. Why is the aldehyde that reactive?
Is this the top of the list?
What list?
The naming list?
Okay. Which is a fair guess. Unfortunately, no. It's also not at the very top of that list.
Why it's more reactive?
Why is the aldehyde?
To the ketone.
Yep.
Because you're, yeah, sterics.
Sterics. When we look at the aldehyde, we have hydrogens versus carbons. Hydrogens are smaller. There's a much easier access to the kind of the backside-ish of that carbon. On top of which, those hydrogens don't have electrons, which means those electrons, lack of electrons, can't be used to stabilize that positive carbon. Okay? So the aldehyde ends up reacting fairly efficiently through an acetal type process. When we move to the ketone, though, our reactants are favored. Okay? Why? We've now changed the reactivity of the electrophile. Okay? That shift is just enough that we don't get a lot of acetal formation. Okay? What happens when we move to the last one? Still a ketone, still an acetal.
You have a ring structure.
We now have a ring structure. Okay? If we look at numerics, 2 starting materials and 2 products. Okay? So entropy is now not a counteracting argument in this one, and we get a little bit of stability due to the ring structure. Guess what all carbohydrates are?
Ring structure.
Ring structures. Why? Because they're more stable. Okay, so when you talk about acetals, you have to be able to identify where an acetal is. So where's the acetal? What makes the bottom structure an acetal? Or any of the acetals acetals?
The 2 OH groups?
2 OH? 2 ethers is a little bit better. Okay. I have a carbon that is bonded to 2 oxygens. Those oxygens are also bonded to carbons. So it's 2 ethers. So the compound I know without hydrogens in an acetal down here. Does it have 2 ethers?
Yeah.
Yes. Is it an acetal? No. So it's not just that it has 2 ethers, it's that those 2 ethers share 1 carbon. Okay? That has to be your central underpinning. Okay? So there's all that. This one I didn't read, but I didn't get through it. Did you guys identify acetals, hemiacetals in the video? For those people that did it?
No, I don't think so.
No.
Didn't do it? Okay. We'll pick up here on Wednesday, okay, with identifying those. I would highly recommend you do that because I don't want to spend a whole bunch of time identifying our acetals and hemiacetals.
When? On Monday?
Okay. Monday, whatever. The next time we meet.
Is it Wednesday?
I don't know.